Hi, in this video, we want to take a look at latent growth models. All right, so this example is taken from Modern Psychometrics by Mayer, and here's the GitHub page to get the code. This textbook can be downloaded for free through the University of Central Florida's library if you're a student, or if you go in person. It's a really good book. I recommend it, and it's got a lot of good information about psychometrics. All right, so latent growth models. So here, what we want to do, we want to look at longitudinal changes when we're using latent variables. All right. I mean, does that make sense? Longitudinal growth. Yeah. All right. So in the simplest form, what we're going to do, we're going to have a latent intercept and we're going to have a latent shape. All right. So for us, since we're looking at longitudinal things, a time reference point of 0, starting point, the intercept is going to be like our starting point for things. All right. Now, as you look through all the code on this, you'll notice, and all the loadings also, you'll notice that there's going to be a lot of zeros and a lot of ones popping up. All right, that is intentional. So there's going to be like reference points and like loadings that are used to basically give us, in relation to each other, information about what's going on. And so when we see a 0 and we see a 1, that's an indication that that's really like a reference for other items going on in the analysis. All right, so in latent growth modeling, we typically fix the latent intercept loading to 1, and this is akin to having a 1 vector in our linear regression fitting matrix. Now, for the shape, we have options. We could simply fix the first loading to 0. And so this reflects the initial time at 1. And so the intercept factor will be based on the time 1 measurement. Now, for identifiable reasons, we need to restrict one more shape loading also. And so we'll fix another second loading to 1. And while keeping all the others open. Now, we do this really for mathematically for things to work out. And so what we're doing when we set these particular values, we're saying these are the ones that we use as like benchmarks to reference the other items. Okay, so if you look through this, we could go through this process and get the same results using mixed effects models. Now, there's advantages and disadvantages in both ways. So in latent growth modeling, really, it has a lot of flexibility. I mean, latent growth modeling has a lot of flexibility to it. And so I find that very appealing. We can get like extensive fit statistics and parameter testing. It is easy peasy lemon squeezy using the Latent package. And we get like pretty detailed specifications of our covariance structures. And this is actually the part that I like the most. Maybe I'm just nerding out over the whole covariance thing. Maybe I've just taught regression enough times where I had to say 0 covariance between observations and constant covariance or constant variance. I've said that so many times that deviating away from that just feels appealing because it's something different. But it's not all rosy on this, for the latent growth modeling. A shortcoming is that we have to have, balanced design. And if we don't have balanced designs, then we need to start doing things like imputing or like chopping, parts of our data off, filtering it so that we do have the balance, which is definitely a disadvantage to it. Neither one is what we want to do. If I'm imputing, I'm making synthetic data, which, is, definitely a circular reasoning could be going on and could also make people question my output. If I filter the data to make it into being balanced, then I'm not using everything I recorded. And that could be a huge data loss. Now, if I'm using mixed effects models, I can things can be unbalanced, boom, just like, your X, unbalanced. Okay, so mixed effects models are better at handling a wider variety of response types. All right, that's definitely an advantage there. And that comes from the whole latent variable, like principal component-ish fitting aspect. And mixed effect models make it easy to incorporate autocorrelation structures and other aspects of time series into our modeling. And so if we're going to want more of a time series feel for it, mixed effects models is going to be the better choice. All right, so now let's go ahead and load our data. So in the aspect package of R, there's the Duncan data set. And so here, this takes a look at marijuana, cigarette, and alcohol consumption. And it puts everything on a 5-point scale. So really, it's ordinal data. And for one of the later models, we're going to want to use alcohol in there as a covariate for another, I think, marijuana. So what we're going to do, we're going to go ahead and do some feature engineering and get the row means for the alcohol columns. All right, so what we're going to do now, we're going to do a simple latent growth model. All right, so check out the intercept term. So here's my intercept term. I've got a 1, a 1, a 1, and a 1. Does that feel like something from classic regression when we're doing our matrix algebra? Yes, we have a column of all ones. So, this is akin to doing that. Now here, and realize that this is T1, T2, T3, T4. That, specifies the longitudinal aspect of the data. Now the shape, you'll notice for shape, I've got 0, 1, then nothing, nothing. All right, so here, this is like 0 and 1. It's like a linear increase. And then these guys are free to be whatever. So the 0 and the 1 are working out to be the baseline. Now, mathematically, we need to put down 2 to be able to fit the rest freely. And I'm not going to really dig into the output from the models. I'm just going through and spitting out the code that I would be looking at if I was going to start like digging into these. I mainly want to emphasize the model structure. And so that way, if you're working on a project and you want to do latent growth modeling, you know how to build your models with your data. And here is the path. I always like looking at the path. I find that, so something I find juicy about this type of modeling are the path figures. And here, as you've seen in the other videos, I really would not present these this way. For the parameter estimates, I would take each of the manifest equations and I would present the confidence intervals in a plot. I would take the covariance, or residual covariance equations, and I would put them in confidence interval plot. And the same thing for the intercepts. Put it on confidence interval plots. That way, it's easier to interpret what's going on. And you'll notice as I look through, a bunch of the estimates are 1s or 0s, and that corresponds to what we've set up earlier. So when I look up here. And now, if we want to, we can look at the fit measures to spit it out. Now, when I get more exotic forms of the model, I'll have more things being spit out. So you'll notice that the number of terms that are coming out from the fit measures function will change depending on the model structure. Now let's take a look with linear trend on consumption. All right, so here I've got 0, 1, 2, and 3. So here you can see that that's a linear trend, increasing. But here I've got 1, 1, 1, and 1. So over here, what's happening is the intercept is still all 1s, but on my linear trend, I no longer have the flexibility on the values that are appearing here. They have to be with that linear trend. And here we can see the linear trend values right there very nicely. And here are our intercepts. All right, so now let's go ahead. If we did linear, can we do quadratic? Yes, we can. All right, for the quadratic, once again, we go 1, 1, 1, 1, intercept, perfect. Then linear, 0, 1, 2, 3, just like before. But quadratic, we're squaring the ones for the linear term. So 0 squared, 1 squared, 2 squared, 3 squared. Boom. And you can see the diagram gets a little bit juicier with this. We have, quadratic going on. And we can see in our estimate these values coming up. And when I have the estimated values are fixed that we're specifying them, you notice that the standard error is always 0. Well, standard error 0 means z value doesn't make sense, p values don't make sense, and my confidence intervals are fixed values. So we're making the assumption when we enter these that we have perfect measurement for it being 1, 1, 1, 1, 1, 2, 0, 1, 2, 3, or the squared values. The rest have statistical properties and confidence intervals and z-scores and all that beautiful, beautiful stuff. All right, so now let's go ahead and let's extend the latent growth models in another manner. Let's go ahead and let's say that we want ordinal manifest variables. Okay, so here, that is a very interesting operator. And so this is a threshold operator if you look through the Latent package documentation. So notice that this is the operator for manifest variables. The single tilde is for regression. Double tilde is for residual covariance. And then boom, we have threshold. And you'll notice it's similar to here. Now, the convention in the Latent package is that for the thresholds, I have to go T1, T2, T3, T4, and so forth, just like this. Now, something that's important to realize is that we have to specify some values for the same mathematical reasons that we did previously. And so we just go ahead and put 0 on the first one, and we know that the first value is going to be our reference point. And you'll notice we get loading, or excuse me, threshold operators here. And when we specified 0, we don't have any we have 0 standard error. So, it's operating like that is perfect measurement, and that is our reference point for the other ones. So always remember that when I specify the value and other ones are open and free, really we're setting it up so that we're comparing the reference value to the others, or the other values to the reference. All right, so another thing we can do is that we can go ahead and say that we want our manifest variables to be continuous. All right, and we've actually already done this, but we're going to go ahead and include marijuana with a linear trend. And just to make it a little bit more interesting, we're going to specify correlated errors across subsequential time points. Now, without any further restrictions, we would have a problematic case. So to avoid this, we're going to restrict the error variances. And so we just go through and we're going to fix the error variances here. Here we're saying that we have covariance relationships on the residuals. And here we have continuous manifest variables. And there's plenty of stuff to like dig in if I'm really getting interested, if I feel like I've got something good going on. Now, for this next one, I want to build a model to see if alcohol consumption influences marijuana. All right. So I mean that's something that I heard growing up was that, teenagers start drinking, and drinking leads to marijuana. Marijuana is a gateway drug. I don't know if this is true or not, is what I was told. That we, as statisticians, we can actually go get data and evaluate it. And this is one way that we could check this part out. So you'll notice here, remember that we created the row means for alcohol. We're going to say that the pot intercept and the pot linear terms, we're going to do regression with that one single average of alcohol. Okay. Now, of course, we can also do it with, more than, we could do more columns included in the alcohol if we wanted. But here we're just taking the average overall just to see what happens. I think it's probably a poor model structure because here we're including alcohol 4 to model pot 1. So longitudinally, that doesn't really make sense. So, but yeah, whatever. The model ends up being a poor fit, so it might just be bad model structure. And so you'll see here, we get on our regression term, we get our pot intercept and our pot linear terms are being modeled by the average alcohol score. And here we have our regression formula terms. And you'll notice I've got more stuff being spit out when I do the fit measures. So I want to go in and start digging in. All right, so now let's go ahead and make this a little bit more interesting. Let's include alcohol as time-dependent covariate associated with marijuana consumption. So now you'll notice I'm going that pot regression-wise depends on alcohol for all 4. Okay. Does that seem reasonable? Yeah. Now, another one that might be reasonable would be that, pot 2 depends on alcohol 1. And then, pot 3 depends on alcohol 1, alcohol 2, or maybe just alcohol 2. So, we may want to do a lag factor aspect. But, this is definitely interesting. So here we would be looking at, pot and alcohol manifesting at the, being manifested at the same time. So here we'd be saying that if somebody is smoking pot, then they would not discontinue drinking alcohol probably. And we get a way more interesting path diagram. We get plenty of stuff spit out here to look at. All right, I hope that this has been informative. I hope this excites you. I find this stuff to be really interesting. Well, that's all I've got for you. Take care and goodbye.